now that we've established just a very basic idea of an exponential function, we've seen the exponential growths, and that's when the base is greater than 1, and we've seen the exponential decays, where the base is between 0 and 1. Remember, we really can't have a base that's 1, right? If you had a base of 1, c times 1 to the x, well, that's just really c, because 1 to the x is 1. And that just ends up being a constant function or a horizontal line. Not very interesting. We've seen that before. It is an interesting function, but it's not exponential, I should say. It's not an interesting exponential function. So it reduces down to a line. So we don't want 1 as our base. We also don't want 0 as our base. If we had 0 as our base, we'd have c times 0 to the x. Well, 0 to the x is 0. And c times 0 is 0. Everything zeroes out. You also get a horizontal line, but it's right on the x-axis. Again, an interesting function, but not exponential. It doesn't really, give us these cool behaviors, growth or decay. And of course, if your base is negative, which is also the other thing not included here, if a is less than 0, you get some weird things that happen. In fact, you get an undefined value at some points, or actually get complex numbers as outputs, because you'd have negatives. So let's say like you had a -4 as your base, right? C times -4 to the x. Well, that seems fine, but when you plug in if you plug in even values, you'll get positive outputs. If you plug in negative values, you get negative outputs, so you get a graph bouncing all over the place. If you plug in fractions like 1/2, it's undefined. It's actually a complex number, right? It's 2i. If you do a 1/2, because that's a square root, and you can't do roots, square roots with negatives, unless you're going to incorporate complex numbers. And we don't want to do that. Complex numbers aren't graphable like this, using a real number system. So, or real, two real axes. So we can't really work with those. So we don't want a to be -, 0, or 1. So we say a cannot be less than 0, a cannot equal 0, and a cannot equal 1. Those are 3 different types of numbers that are all invalid as your base. Okay? So your bases have to be greater than 1. They have to be between 0 and 1 to be considered an exponential function. Okay. Now, we can also perform transformations on these functions. We've seen transformations, your vertical and horizontal shifts, your vertical and horizontal compressions, and your reflections, both vertical and horizontally. And so, if I were to take a function, this is a exponential growth. If I was to multiply that exponential growth by a negative value, if it was like -c times a to the x, where again a is bigger than 1, then the graph here would reflect across the x-axis, and it would be a growth still away from the x-axis, but going downwards, decreasing this time. It's like a decreasing growth. It's kind of weird. But it's because it's on the negative side. And of course, if we had exponential decay, but again multiplied by a negative, our graph would then reflect across the x-axis, and it would be an increasing decay, which is kind of weird again. It's a decay because it's getting closer to 0, but it's on the negative side. So, whether you call it decay or growth is maybe a little bit weird, but it's an increasing function rather than a decreasing function, yet still has the same horizontal asymptote. We can also shift these graphs around. By shifting the graph vertically, you're actually going to change the range of the function. And a vertical shift. Oh, green marker's not working. If I went with y equals c times a to the x plus 5, for instance, that's just going to raise the graph up 5 units. So the horizontal asymptote would actually be up here 5 units high, okay, wherever that vertical shift is. And of course, if you lowered it, if you did subtract, -7 or something, then that asymptote would be at 7, and you would have a range then 5 to infinity here, so everything above 5. And of course, if it was shifted down 7, for instance, and -7, it'd be from -7 to infinity, everything above that. And of course, it doesn't change a whole lot if I go over to my exponential decay. Then you just have a decay function that has that shifted horizontal asymptote. Now, if I wanted to do, let's say, a horizontal shift of the graph, well, that's not going to change the asymptote in the range. That's actually going to change the y-intercept, okay? So if I think about that, if I wanted to do, I'll do that over on the decay function. So let's do y equals c times a to the, I don't know, maybe x minus 2, for instance. Well, here, we're going to be shifting the original graph 2 units to the right, right? X minus 2 is a shift right 2 units. And so instead of the c value being here at the y-intercept, that being c, that c value just gets moved over 2 units. But the rest of the graph is the same. Oop. Okay, so it ends up changing the y-intercept. The y-intercept now moves. This is c over here, so that'd be at 2 comma c rather than 0 comma c, and then the y-intercept is going to be different. And how would you find the y-intercept? Well, you'd have to plug in 0 for x. It would be c times a to the -2 power. Okay, so just a different change, but again, your range, the range on this one is still going to be from 0 to infinity. It's still just your positive numbers. Your horizontal asymptote doesn't change; it's still on the x-axis. Okay. So just a few things that you might see pop in from here from time to time. Another thing you might notice excuse me, is that the horizontal reflection is kind of an interesting transformation. It'll tickle my throat. So the horizontal reflection is interesting. If I were to take y equals c times a to the -x power, that would be your horizontal reflection, right? Replace x with -x. Think about that in this case. Here, if you reflect horizontally, you take the increasing part and flip it over to the left side, and the asymptote and flip it over to the right side. Well, what do you get? An exponential decay, right? It looks like this graph. And in fact, it is the same thing. Basically, if you start with an a value greater than 1, stick a negative exponent on it, that flips it and makes it less than 1. Kind of interesting, which is what's over here. And vice versa. If I were to take this base, the exponential decay, and multiply it by a negative on the inside, so power becomes negative, then you end up with an exponential growth. Okay, so imagine flipping that horizontally. Okay, and so what you'll find is that on occasion, we're going to start with a base that is greater than 1, and then just stick a positive or negative exponent. A positive exponent will give us a growth, whereas a negative exponent would give us a decay, which is kind of interesting. So a different way of looking at it. Again, if your base itself is greater than 1, you get growth, less than 1, you get decay. But if you then alter the sign on the exponent, you get the opposite effect. Okay, so just a couple different features of transformations that I think are important for you moving forward.